Hello and welcome to this course on MATLAB programming for numerical computations. We are in week 10 of this course. In the first 3 videos of this week, we have covered ODE boundary value problems. Now we are going to go to a different nature of problems called differential algebraic equations. What do we mean by differential algebraic equations? Differential algebraic equation means some of the equations are of differential type, some of the equations are of algebraic type. That means you have ODEs combined with algebraic equations. So you have something that you have learned in week 7 and week 8 combined with something that you have learned in week 5 of this course. I will give you a few examples so that you get motivated towards understanding why DAEs are important problems. Again, for a lot of times in the first couple of years of your undergraduate, you are not going to encounter differential algebraic equations. It's only in the latter part of your undergraduate curriculum do we actually introduce you to DAEs. That also sometimes, not always, only in a few courses. However, this is quite an interesting and an important topic, and that's why I'm covering that in this particular lecture series. Okay, so as I said, we have covered algebraic equations of the nature gx equal to 0 in week 5. We have covered differential equations of the nature y dash equal to f of t comma y in week 8. Okay, let's say we have y as nothing but yx, okay, such that we are given dy by dt equal to f of t comma y and 0 equal to g of t comma y. Okay, that is what differential algebraic equations are. So we can erase this and we can write this as this as well. So this is the nature of differential algebraic equation. We usually don't have t in this equation. Okay, so finally the differential algebraic equation is going to be of this nature. Again, to keep consistent with the way we have represented our equations in this MATLAB course, I will use this capital Y. Okay. The variables that appear under the differential sign, okay, are differential variables. So differential variables are y. Anything that does not appear in differential variables are called algebraic variables. So for example, if you have dy by dt equal to x minus y, okay, and we have 0 equal to y cube minus 3y plus 2, okay. Because y appears in this equation, y is a differential variable. Even though x doesn't appear in this equation, x is implicitly defined by this equation and x becomes an algebraic variable. Okay, so this is an example where x is implicitly defined. Okay, implicitly defined, indirectly defined, that's actually quite fine. Okay. Oftentimes the equations are going to be dy by dt equal to x minus y and 0 equal to something like x cube minus 3y plus 2x minus 5, okay, and that becomes where an example where x and y are explicitly defined. Okay. So in this particular case, y is the differential variable, and irrespective of whether g is of this nature or this nature, x is a differential variable. Okay. Again, I don't want to be pedantic, I don't want you to really think about these definitions, x is differential, y is differential, none of that. What message I want you to take away from all of this is that there are certain variables that are represented in the form of dy by dt equal to right hand side and certain variables represented as 0 equal to g of x comma y. Okay. So that's really the primary takeaway from this. Okay. I will now take certain examples because I'm fairly sure some of this might be a little bit confusing to some of you. Okay. If you have done differential algebraic equations before, you will actually find the discussion that I am going to have fairly useful in understanding some of the intricate concepts in DAE. Okay, so let us consider first example. The first example is y dash equal to x and 0 equal to x minus y sin t. Okay. This is an example of DAE where y is the differential variable, okay, because y appears in the form of y dash and x is a algebraic variable. Okay. This is another example. Okay. This is an example where y dash equal to x, just as before, and as before y is differential variable. Okay. And even though x does not appear over here, but x does appear over here, so x is an algebraic variable. Okay. Actually, the more appropriate or less confusing way to say is x and y are DAE variables, or technically more correctly are dependent variables of a DAE. Of these, y is or y are differential variables. So, this is the less confusing interpretation. Okay. However, both these interpretations that I have over here are both very much valid. Y is differential and x is algebraic is very much valid, or to say x and y are DAE independent variable, sorry, x and y are dependent variables of a DAE, of which y are differential variables, is also equally valid. Okay. So, next we will come to an interesting concept, that is an index of the DAE. Okay, what is the index of the DAE? Is if you look at the if you look at the algebraic equation, it is the number of times that you need to differentiate an algebraic equation so that all the variables become differential variables. Okay. So, formal definition, index of a DAE is number of times you need to differentiate g of x in order to convert algebraic equations into differential equations. Okay. What do we mean by that? If we take this particular example and we take d by dt of this, we are going to get d by dt of this equation is going to yield us 0 equal to dx by dt minus sin t dy by dt plus y cos t. Okay. You take sin t plus y cos t on to the other side, and we will be able to write this as this. Now, dy by dt is nothing but x. So, you have dx by dt equal to x sin t plus y cos t. Okay. So, dy by dt equal to x and dx by dt equal to x sin t plus y cos t makes it two differential equations in two unknowns. So, the index of the first equation is 1. Now, let us look at the second example. In second example, let us differentiate this guy. What are we going to get? We are going to get 0 equal to dy by dt minus sin t dy by dt minus y cosine t. Okay. Now, this again does not have x dx by dt yet. Okay. To get that, what we do is we realize that this is x, this is x. So, we will write it as 0 equal to x 1 minus minus y cos t. Now let us differentiate it the second time. We will get 0 equal to 1 minus sin t dx by dt minus x cos t minus dy by dt cos t plus y sin t. Okay. So, if we take this guy on to this side, we are going to get equal to this plus this minus this. Okay. And then we can divide it by this guy and we will get and dy by dt is replaced by this. Okay. And therefore, we will be able to write this as 2 cos t minus y sin t divided by 1 minus sin t is dx by dt. And that is the reason why this example is Index-2 DAE. Again, why is this example Index-2 DAE? Because we took the algebraic equation and differentiated it twice in order to convert the DAE completely into ODEs. Okay. So, that is the definition of index. Okay. Now, let us take one more example. Okay. This example is of a pendulum. Okay. So, we have this pendulum, okay, and that pendulum is swinging, okay, and at any point of time we are doing a force balance on this pendulum. Okay. So, what we have is the gravity is acting in this direction, there is a tension. Now, when we have all of this defined, the Ty is in the negative direction, Tx is in the negative direction. So, we will put the sign conventions over here. Okay. So, now when we overall do the force balance in the vertical direction and force balance in the horizontal direction, we get these two equations. Okay. Now, there is still a problem. Now, what is that problem? The problem is we have not yet defined the tension per unit length in the string. Okay. Now, how do we go about this particular definition? Okay. One is we can go on to polar coordinates and make the definition. Other is we do not define it explicitly, we define it implicitly. Now, how can we define implicitly? Now, this pendulum, let us say, is attached to a rigid body. Okay. If this is a rigid body, that means this pendulum is going to go in a circular arc only. Circular arc of radius equal to the length of this rod. Okay. If the length of this rod is L, oops, I had written R. If the length of this rod is L, then you will have L square equal to x square plus y square. Okay. So, this becomes a DAE where you have differential equations and you have algebraic equations. Okay. Interested readers might actually check that this is an example of an Index-3 DAE. Okay. So, if you want to solve it in its native form, we will have to use certain high index DAE solvers which are not very commonly available, but there are some high index DAE solvers. We are not going to cover that in this particular course. Okay. Now, is it always that this equation is going to result in a DAE? Well, not necessarily, and that is where the trick that we have learnt in our high school comes into picture. Instead of solving this in Cartesian coordinates, we can solve it in polar coordinates. Okay. In polar coordinates, what happens is that you have the tension in this direction, as against that you have acting in this direction, you have mg cos theta and mg sin theta. Okay. Now, because this ball is not going to move radially at all, okay, what do we have is dr by dt equal to 0. Why? Because this ball is not moving radially. Now, why is this ball not moving radially? The ball is not moving radially because the tension in the string exactly balances mg cos theta. Okay. And if you substitute that and you take the consideration that the angular momentum, or sorry, the angular acceleration is only caused by the mg sine theta component, you will get this particular equation. This is something that you have done in high school. Okay. So, in Cartesian coordinate, what you get is a index-3 DAE, and in polar coordinates what you get is an ODE. Okay. That is basically what we are going to get if we define the pendulum problem using physics that we have learned in high school. Okay. So, to recap, what we have done is we have talked about DAEs, we have defined the index of the DAEs, we gave a practical example of pendulum to show that pendulum results in a high index DAE problem, but the same problem, if you convert it into polar coordinates, you are going to get a ODE. Okay. Lot of times you are able to convert DAEs into ODEs, but not always. There are several hundreds of examples of practical interest where you cannot convert DAEs into ODEs. There are hundreds other problems where of course that conversion is possible. Why we need to learn DAE solving techniques is so that we can apply it to this myriad problems that we will encounter where the structure of the problem is a DAE and they need to be solved using a DAE solver. Okay. Now, what is the structure of the DAE problem? Okay. So, let us look at this particular example again. Okay. As we said, y is defined as yx. Okay. Therefore, we can write it as okay. This is the standard problem. Okay. What is M? M is going to be a 2 by 2 matrix. Why? Because dy by dt is a 2-dimensional vector, right hand side is a 2-dimensional vector. So, therefore, you need to have a 2 by 2 matrix. Okay. Okay. Now, what is the first equation? The first equation is dy by dt plus 0 multiplied by dx by dt. Okay. That is going to be equal to f of t comma capital Y. What is going to be the second equation? The second equation is going to be 0 multiplied by dy by dt plus 0 multiplied by dx by dt equal to g of t comma y. Okay. If you look at this particular equation, in week 8, the M was an identity matrix. Okay. That was what we covered in week 8. Okay. For DAEs, M has the form I 0 0 0. Okay. Where I is ny dimensional identity matrix and 0 is the nx dimensional 0 matrix. Okay. Do not worry about what I just said. This is the last thing that I am going to talk about in this video. In the next video, I am going to cover a numerical example. That is when you will learn how to do this using MATLAB. M is known as a mass matrix. Okay, and ODE 15S, which is our friend from week number 8, can also be used for solving differential algebraic equations. Okay, so with that, I come to the end of this video. In the next video, I will take up an example. The example that I am going to take is going to be what is known as the Robertson problem, and this is the example of Robertson problem. Okay, the Robertson problem will have the mass matrix, which is going to be a 3 by 3 matrix. Okay. Now, between this video and the next video, think about how this particular matrix is going to look like. Okay. With that, I come to the end of this video. I will see you in the next video where we will solve a DAE using MATLAB's ODE 15S solver. Thanks for watching this video. See you and bye.